Everybody, physics is kind of a big deal. The goal of physics is nothing less than to figure out how everything in the universe works. The concepts and the equations that describe the physical reality that we live in. One of the tricks that we have to do that, to figure out some of the equations, at least in their basic form, is called dimensional analysis. Now, dimensional analysis, that might sound like we're entering the fifth dimension of space-time or something. It's nothing like that. It's really just about counting units and making sure that the units of the equation that you're working with actually make sense. Let me give an example. The most famous equation in physics is E equals mc, and I just can't remember. Is it mc squared or is it mc to the fifth? I don't know. So it's mc to some power. And I'm trying to figure out what that power p is. It's something unknown. I can just use the units on both sides of the equation to figure out what the power has to be. Okay, let's see how this works. If an equation is true, then the units on both sides have to be the same. So in this case, I'll look at the units on the left side, and when I take the units, what I'll do is just draw a bracket on it. And the bracket means I just take the units of that expression. And I do the same thing on the right side. If the left equals the right, then the units of the left have to equal the units on the right also. So what are the units of energy? Well, one thing we might remember is that energy, that's work, that's force times distance. Okay, so energy is force times distance. That means the units on the left side are newtons multiplied by meters. Careful now, that's not newtons times mass. This is just the units on the left side. So it's force times distance. Okay, on the right side, it is mass, that's kilograms, multiplied by c. C is the speed of light to some power. So speed is meters per second. And I don't know what power to raise that to. I'm calling it P. All right. Now, I need to break down the units further because newtons, that's not a fundamental unit. Newtons, remember, are determined by mass times acceleration. So newtons really means kilograms multiplied by meters over second squared, multiplied by the other factor of meters gives me meters squared over second squared. Okay, now I can compare the left and the right side. I've broken it all down into the most fundamental units. So kilograms cancels, and I'm left with m squared over second squared is equal to m to some power over seconds to some power. The conclusion is that the power must be equal to 2. In other words, just based on units alone, just based on the dimensional analysis of the equation, I know that it's actually E equals mc squared. Of course, you knew that anyway, but you see, you can figure out equations just based on the units on both sides. What it doesn't tell me is it E equals 1/2 mc squared or what, So it doesn't tell you exactly what the equation is, but it tells you the right power of the terms that appear. That's example one. Let me give another example. In Physics 223, you'll talk about oscillations, vibrating objects, like this mass that's vibrating up and down on a spring. And you'll learn then that the equation for that vibrating mass is given by y equals a sine omega t. Never mind all the details. T is time, and it tells me the position of the mass at any moment in time. The question I want to answer is, what must be the units of omega? This looks like a W. It's actually a Greek letter, omega. I want to know what its units are. Well, let's do dimensional analysis on it. I know that the units of omega times t must be equal to radians. Must be radians, sine of something in radians. Now, let's break down the left-hand side. I have the units of omega multiplied by the units of time, which that's in seconds. It tells me that omega, whatever it is, whatever exactly it represents, the units of omega must be just exactly radians per second. Radians per second. So that's what dimensional analysis is all about. You have an equation, you check that the units on both sides match each other. It's helpful to check your work. You've written down some equation. Does the equation even make sense? The units have to make sense, and you analyze the dimensions on both sides to see. Or you are trying to remember some equation, and dimensional analysis can help there as well. Next up, unit conversions. Everyone's favorite topic, but you have to face it because people have all different units they like to use. There's the standard, the international standard of units, the SI system. But even within the SI system, some people are going to use the MKS system, that is meters, kilograms, and seconds for their basic units to work with. Others are going to use the CGS system, where it's centimeters, grams, and seconds. So even there, within the SI system, there's conversions that have to be used. It gets, of course, that's just the tip of the iceberg. Of course, some people want to use pounds for force. Others want to use newtons. And then sometimes people want to use what are called dynes, D-Y-N-E-S, a different unit of force. So inevitably, we have to have the skill of knowing how to convert from one system of units into another. Let me just give an example of that. The example I'm going to give is familiar from chemistry. There's the ideal gas law, PV equals nRT. And I'd like to first figure out what the units of this constant R must be. And then I want to convert it into another system of units that you often use. So the question is, what are the units in order to convert them? First, what are the units of R? So this is now dimensional analysis. So R, it must be the same thing as PV divided by N times T. And so what are the units of that? Well, it's the units on both sides. Remember, the brackets just mean I'm just checking the units of it. Well, in standard units, P is pressure in pascals. So this is pascals. And V is volume, that's cubic meters. And then N is the number of moles of gas. And T is the temperature on the Kelvin scale. Okay, so that's the units for the gas constant, at least in the standard system of units. Now, sometimes instead of working with pascals and cubic meters, some people want to work with not pascals, but atmospheres of pressure, and not cubic meters, but just liters of volume. Okay, so in the standard units, the value of R is 8.314, and then it must be pascals times cubic meters over moles times kelvins. Now, usually you say joules per mole Kelvin with the ideal gas law. You can pause, I would pause it right now and check for yourself that pascals times cubic meters, those units are the same as joules. That's an exercise in dimensional analysis. Pause it, try it for yourself. I'm going to move on, and I'm going to convert this. I'm going to do a unit conversion into liters times atmospheres, just so we remember how it goes. So I take 8.314, and then I have pascals times cubic meters over moles times kelvins. And then I have to multiply it by the right conversion factors. So 1 Pascal is just a tiny fraction of an atmosphere of pressure. Or in other words, atmospheric pressure is actually very large. In fact, 1 atmosphere of pressure is like 100,000 pascals. The atmospheric pressure on you is like 100,000 apples weighing on you, and that's a huge amount of pressure. So in other words, the conversion I need to insert here is that there's a conversion. 1 atmosphere is about 101,000 pascals. Okay, so I want to replace pascals with atmospheres. So I'll take 1 atmosphere. 1 atmosphere is the same thing as about 101,000 pascals. Okay, and notice how I put pascals in the denominator, so it'll cancel the pascals in the numerator, and I'll be left with something in atmospheres. Okay. Next up, I need to multiply by another factor, which will convert cubic meters to liters. Now, a liter is about 1,000th of a. It's exactly 1,000th of a cubic meter. Okay, like a liter bottle of water, it takes 1,000 of those to fill up a cubic meter. So I have to multiply by the right conversion factor. Do I do meters cubed over liters, or is it liters over meters cubed? Okay, I need to cancel out cubic meters, so I better put liters up in the numerator and cubic meters down the denominator. That way it'll cancel cubic meters and give me liters. The only question is, what's the number that goes in here? Well, 1,000 liters is the same as one cubic meter. Okay. So multiplying those factors in, dividing by 101,000, and then actually multiplying by 1,000, it gives me 0.08214, and then it's liters, atmospheres over mole Kelvin. And there you go. That's how you do a conversion of units. You multiply by the conversion factors that are appropriate. Notice that I'm really just multiplying by 1. This number in brackets here is just equal to 1. And this number in here is also equal to 1. So I haven't changed the actual meaning of the expression. I haven't changed what it is. I've just multiplied by 1 in a form that shifts from one set of units into another. Next up, significant figures. Everyone's second favorite topic behind unit conversions, I know. But it's actually extremely important because significant figures are all about confidence. And we all want to be confident when we give some kind of scientific result. Science is all about scrutiny, and people are going to look at your measurements and look at it very carefully and possibly criticize the measurements that you've made. So it's important to have confidence in what you've measured. Let me give an example. So when you work with significant figures, sometimes you are adding numbers together, and you got to handle the sig figs there. Sometimes, or I should say adding or subtracting. Sometimes you're multiplying or dividing the numbers, and there are 2 different rules that have to be followed depending on which one of those you're doing. So let's look at adding first. For example, in a lab, you might have to figure out the length of a pendulum. And finding the length of a pendulum involves adding the length of the string plus the radius of the bob on the pendulum. So you might take a ruler and measure the length of the string, but you might have to use some calipers to measure the radius of the bob part of it. So you're going to measure this thing, and it's going to come out to be 0.373, say meters or whatever, for the size of the bob, plus the length of the string, which you used a ruler for, which comes out to be 7.41. Okay, so I add them up, and I get 7.783 for my length of the pendulum. Now, I cannot leave the answer that way. The reason is I used a ruler to measure the string. And what that means is, although I claimed that the length of the string was 7.41, what I really mean is 7.40, maybe up to 7.42. I'm fairly confident it's 7.41, but I'm just fairly confident in that last digit, not absolutely confident in it. Okay, so what that means is when I add them together, this very tiny fraction of a meter that's right here at the end has to be dropped off, because I sure don't know, what I really know is it's 7.7, it could be 7.77, or it could be 7.79. That's what I really mean when I report my answer as 7.78. It's somewhere in that range. Okay, so if I want to report my answer confidently, which we want to do, then I have to respect the significant figures and I have to round it appropriately to 7.78. Okay, so the way to remember this is when you add or subtract, you just look at the back. Okay, that's my rhyme to remember. Add or subtract, look at the back to figure out the sig figs. You just look at the back of the of this number, 7.41, and you look at the decimal place. You look at the decimal place that you're least confident in, and that determines what your it determines how to round your answer. Okay, add or subtract, look at the back. You just look at that that last digit in your least confident number. Okay, multiplying, if you have to multiply or divide numbers, then the rule's a little bit different. So for example, suppose I have to take 10.0 and multiply it by the number 0.3. Now, of course, our calculator will tell us that the answer is 3.0, but that's not actually correct in terms of measurements. You see, when I say 0.3, what I really mean is I'm fairly confident it's 0.3, but it really could be 0.2 or 0.4, in that range. So in that range, the answer is not really 3. The answer is somewhere between 2.0 and 4.0, right? So I sure can't claim that I know the number is 3.0. In fact, I can only keep one, I'm only confident in one digit, which is the number 3. So I have to round it, dropping off that last digit and report the answer as 3. So for adding and subtracting, you just look at the back decimal place. For multiplying, you have to count the number of sig figs in both numbers. 10.0 has 3 significant figures, 3 numbers that I'm fairly confident in. 0.3 only has 1 significant figure. The 0 in the front is just marking the decimal place, and that's not, the 0 is not a sig fig. 0.3 only has 1 significant figure, and therefore, when I multiply it, I can only keep 1 significant figure. So sig figs are a little bit boring, but they're very important because they're all about reporting your answer with confidence and looking at which digits of your measurement you're actually confident in.